Hello again, class. We're going to predict why this insect survived such a huge fall. And today's emphasis is connecting force and motion. Remember, these words may come up like mass, how much matter is in an object, vector, equilibrium, the net, especially net forces, which means the total forces acting on an object. We talk about laws, especially Newton's laws of motion and forces, and perpendicular means 90 degrees. So remember, let's try to explain this insect, why its motion from such a high fall has a smaller impact than a more massive object. Suppose there's a cart resting on a surface and you push it from opposite directions, but it doesn't move. Well, I happen to have a cart right here. Okay, suppose it's resting on the surface. Okay. Something's pushing it this way, and something's pushing it that way. Okay, the forces must be balanced. I can unbalance them. If it's pushed or pulled at a constant velocity, then the contact force on the cart must balance the friction that resists the cart's motion. If a net force acts on an object, it will push or pull in the direction of the motion. This just makes perfect sense, doesn't it? Okay. So, there are ways I could generate constant force. One of them is with this pulley system. If I want to experiment with constant force, I could use that. I could attach a weight to the end of this string and hang it off my table. And of course, my string is a little bit too small, but it fell because I'm generating a constant force. Okay, now let's think of these situations and tell me if the object is accelerating or not accelerating. A car is parked. Not accelerating. All of the motion, all of the forces are balanced if the car is parked. It moves at a constant speed on a straight road. Not accelerating, remember, is a change in the object's speed or direction. A car slows down in a school zone. That is accelerating. It's accelerating in the negative direction if it's slowing down. So it might be going this way, motion that way, but it starts generating a force opposite to its motion. So you could say it's a negative acceleration. You might also say it's a deceleration if it's slowing down. A car stopped at a red light begins to move when the light turns green, accelerating. A car turns a corner at a constant speed. You tell me that one. Accelerating or not? Friction generally acts against motion. However, friction can be the force that accelerates an object in the direction of motion. Like that cartoon character that starts to run but stays in place. And then it suddenly goes. It needs friction to actually start moving, like if you start running on ice. If it's a lower force of friction, there's less force needed to keep it in motion against friction. If you could reduce friction all the way to zero, an object sliding off across the floor would continue at its initial speed without an applied force at all. It would just keep going. Like a hockey puck, maybe. Pew! It would just roll to the end of the hockey court, hockey rink, hockey field, whatever. Newton's first law states that an object at rest remains at rest, and an object in motion continues in motion with constant velocity unless it experiences a net external force. Okay, so this is called an Atwood machine. It has two masses attached by a string connected by a pulley. So here's we could say this is an Atwood machine if I hang two masses from it. Let's see if I could do this. So mass down on the floor. And I get another mass equal to that one. So if I push one down, it'll stay there. Cool. So they're all, it's a motion from balanced forces. If I pull one, the gravity of this mass is pulling down, and it's equal to the tension on the string. And then both masses are experiencing the same force vectors, so it's equal. If I add force to either side, of course, it causes that motion to happen. So each mass is pulled down by gravity and up by the tension in the string. Okay, let's create a model for this. Graph the data and draw a line of best fit. So when the force is 5, a 2 kilogram mass will accelerate in the positive direction to 2.5. So go up to 5 and over to 2.5. When the force is 10, it accelerates up to 5. When the force is 20, a 2 kilogram mass accelerates 10 meters per second. And when the force is 30, a 2 kilogram mass accelerates 15 meters per second. So let's draw the line of best fit for these points. So this tells us that the blank slope of the force acceleration graph shows a positive or a direct or inverse. Direct means one variable increasing also increases the other variable. Inverse means one variable increasing caused the other variable to decrease. A larger net force on a given object produces a correspondingly bigger or smaller acceleration. Let's put bigger or smaller. And this should be positive or negative. Sorry, positive or negative. Okay. So think about that and put the correct words. If there is a greater net force, there's a greater acceleration, which depends on the direction and magnitude of the force. These vectors in blue show the car's velocity before and after a time t, while the dots show the car's position at equal time intervals. So we're going to draw a vector showing the direction of the net force. So let's do that with green. Okay, so the car started with this vector, this small blue, and at equal time intervals, that vector increased to time t. So the net force for the car is in this direction. Now the car started here at a smaller acceleration that expands this way. So we can say the net force is in this direction. If the car started here and each vector at an equal time interval is decreasing, we can say the net force is in the negative direction. And this car started here, going in reverse, and its acceleration is decreasing. So the brakes are applying a net force in that direction. Graph this. Let's do some data analysis here. So let's graph this data and draw the line of best fit, and then we'll choose the best statements. We already did this. Or no, we didn't do this because now we're thinking of acceleration versus mass. So with a constant force of 10 newtons every time, how will changing the mass affect acceleration? So when the mass is 1 kilogram, acceleration is 10. At 2.5 kilograms, acceleration is 4. At 5 kilograms, acceleration is 2. 10 kilograms, acceleration is 1 meter per second. And at 15 kilograms, acceleration is 2/3 meters per second. So draw this line. Shows a logarithmic curve that would probably continue downwards. Okay. So in this one, choose the word that goes in the blanks. The positive or negative slope of a line tangent to the mass acceleration graph shows a direct or an inverse relationship between the mass of an object and its acceleration. When I increase the mass, how does this other variable respond? Does it also increase? That would be direct. Or does it decrease? That would be inverse. So a more massive object acted on by the same net force as a less massive object will have smaller or larger. What do you think? Oops. So if force is held constant, but the mass increases, will the acceleration increase or decrease? A familiar example is pushing a small child or a large adult on a swing. The same force applied to a blank mass makes a smaller change to the motion. What do we think? What would make a smaller change? Same force applied to a smaller or larger? The more massive an object, the greater or lesser force is needed to produce given acceleration. So if force is represented by by F, acceleration by A, and mass by M, how would we show it this inverse relationship? So if force stays constant and I increase acceleration, I would have to decrease the mass. Okay, so lastly, thinking of back to the ant. Why won't it let me? Okay, we'll go back to the ant. Why is the fall of a small lightweight object different from the fall and impact of a more massive object? Use the idea of how mass and acceleration relates to force in your response.